In Chapter 8, we begin inferential statistics. We start inferential statistics with confidence intervals. In this chapter, we will learn to understand and interpret a new distribution called the student's t-distribution. We will identify the appropriate distribution necessary for various confidence intervals. We will calculate and interpret confidence intervals for means and proportions. We will calculate sample sizes needed for estimating population means and proportions at desired confidence levels. And this chapter will allow us to determine an interval for which a population parameter is likely to be in. This is what gets us started with inferential statistics. So, inferential statistics. We use sample data to make generalizations about an unknown population. We can estimate the population parameter with a certain level of confidence. We can use the normal distribution when the population standard deviations are known. When the population standard deviations are not available, we will use a new distribution. This new distribution is called the student's t-distribution. We want large samples when using the student's t-distribution. The larger the sample, the more accurate the estimate will be. If you performed a study and found a sample mean and wanted to say something about the population mean, you could use a confidence interval. Confidence intervals allow you to state with a specific level of confidence an interval in which you believe the population mean is in. Confidence intervals can be done for any population parameter. We're going to focus on means and proportions for this course. A key thing to remember is that the unknown population parameter is fixed. The confidence interval is a random interval based on the point estimate, and the confidence interval may or may not actually contain the population parameter that we are trying to estimate. As stated earlier, we have two distributions to work with when computing confidence intervals. First, the student's t-distribution. This will be used when the population standard deviation is not known. We also want to assume that the population is approximately normal. If the sample is large enough, the t-interval will work even if the population is not normal. The other distribution is the standard normal distribution. This will be used when we have access to the population standard deviation. Again, we do want to assume that the population is approximately normal or that we have a large sample size. The large sample size allows us to not need the assumption that this is a normal sample. Remembering back to Chapter 7, this desire for large sample sizes comes from the central limit theorem. This is what's being applied in order to construct these confidence intervals. So what do we need for a confidence interval? Well, the first thing that we need for a confidence interval is a point estimate. A point estimate is a specific number that is computed from a sample and is used to estimate the population parameter. A confidence interval will always be centered around the point estimate. What else is needed? Well, to create the interval, we have to have some margin of error. This margin of error gives us an interval around that point estimate. To find this margin of error, we need to state a confidence level. Commonly used confidence levels are 90, 95, 98, and 99. We need the sample size from which the point estimate was taken, and we need the standard deviation. Either population or sample will work, and this is what's dictating which distribution we are going to use. So let's talk about using the standard normal distribution for creating confidence intervals. This is done when we have the population standard deviation available. We're going to start with this because it's using that standard normal distribution that we've worked with before. To calculate the confidence interval, we need the following pieces of information: the population standard deviation, the sample mean, this is our point estimate, the sample size, and the desired confidence level. This desired confidence level is going to point us to a z-value. The z-value is what we will actually use in the calculations. The z-value can be found either by using the distribution table or by using your calculator. These are the same methods that we used in Chapter 6, only now we're always going to be looking for the positive z-value. So we'll be looking for the one that's on the right. So let's practice finding z-values using a calculator and by using the table. To find z, we need to identify the area to the left of the z that we are looking for. I've given you this formula here with CL standing for confidence level. That is your confidence level written as a decimal. So 1 minus the fraction 1 minus your confidence level divided by 2 will give you the area to the left. We know that the confidence level is the area in between those red lines there. So the area on the outside is 1 minus the confidence level. On each outside edge, there is half of 1 minus the confidence level. So we have 1 minus the confidence level divided by 2, gives us the area in just one of those tails. So that would be maybe the area in the right tail. And then we want all of the area that's to the left of that red line. If the area to the right of it is 1 minus the confidence level divided by 2, we want 1 minus that ratio. Thus, we have that area to the left formula that I've given you. Now, to find z on the calculator, we would use inverse norm function, stating the area to the left. Then we'd use 0 for the mean and 1 for the standard deviation, because we're in the standard normal distribution here. Remember, this function is found underneath the distribution menu, second bars. To find z on the table, you will need to access the table and search for the area inside. Once you find it, you will locate the z for that area by looking at the row and the column headings. So let's look at an example together. If you want a 95% confidence level, and you know that we have the population standard deviation, what z are we going to want to use for the confidence interval? Using the formula, we have 1 minus the ratio 1 minus 0.95 divided by 2 gives us 0.975. Now let's go ahead and look for it on the table real quick. We find it right down here, which gives us 1.96 for a z-value. Now that's also what you would find if you were to use inverse norm on your calculator. Since these z-values depend only on the confidence level, there's only a few z's that we will commonly use for confidence intervals. Since the confidence levels are typically 90, 95, 98, or 99, let's just go ahead and find these z-values accurate to 2 decimal places. For a 90% confidence level, you would want a z-value of 1.65. For a 95% confidence level, you would want a z-value of 1.96. For 98% confidence level, you'll want a z-value of 2.33. And for a 99% confidence level, you will want a z-value of 2.58. Let's practice here with a confidence level that is not one of our common ones. Find the critical Z value for the confidence level of 96%. So our critical value, using inverse norm function, we have 1 minus the ratio 1 minus 0.96 divided by 2, and then a mean of 0, standard deviation of 1. So we get a critical value of 2.05. At this point, we're almost ready to find our confidence intervals. We need a formula still in order to use, so we can calculate this by hand by using the following formula. Mu is in the interval x bar minus z times the ratio sigma over the square root of n. That's the lower bound. And then the upper bound would be x bar, the sample mean, plus z times the ratio sigma divided by the square root of n. But we don't want to answer like this. Statistics is about presenting information to the public, so let's answer using this general fill-in-the-blank sentence. So I am blank percent confident that the population mean of, or for, fill in what you're talking about, is between blank and blank, where that first blank is filled in by that first lower bound there, and that second blank is filled in by the second bound, your upper bound that you're given. Looking at an example here, suppose scores on exams and statistics are normally distributed with an unknown population mean and a population standard deviation of 3 points. A random sample of 36 scores is taken and gives us a sample mean, or a sample mean score of 68. Find a confidence interval estimate for the population mean exam score, the mean score on all exams. So we want to find a 90% confidence interval for the true population mean of statistics exam scores. Knowing that we want a 90% confidence interval, we know that we need a z value of 1.65. So let's plug everything into our formula. 68 minus 1.65 times the ratio 3 over the square root of 36, and then 68 plus 1.65 times the ratio 3 over the square root of 36. Simplifying each of those numbers, we end up being able to state, I am 90% confident that the population mean for exam scores is between 67.175 and 68.825. Now we can do confidence intervals on the calculator as well. And while doing things by hand is great because it gives us an understanding of what's going on, I do want to encourage you to go ahead and use your calculator as much as you want to. Confidence intervals using the standard normal distribution will use the function z-interval. This is found by going to stat, then over to tests on the TI-83 or 84 type calculators. The calculator will then ask you for the mean, the population standard deviation, sample size, and C level. C level stands for the confidence level. Be sure to use the decimal form of the confidence level. For example, if you have a 90% confidence level, you'd want to say that the C level equals 0.9. So if you were to measure 34 textbook weights and find that they have a mean weight of 56 ounces and assume that the population standard deviation is 7.7 ounces, based on this, you could construct a 90% confidence interval for the true population mean textbook weight. We could use the z-interval on the calculator and we would enter that sigma equals 7.7, x bar equals 56, n equals 34, and C level is 0.9. You would receive the following output. So you could write a sentence stating, I am 90% confident that the population mean for textbook weight is between 53.83 and 58.17 ounces. Now let's talk about doing confidence intervals with the student t distribution. Remember, we are going to use the student t distribution when the population standard deviation is not available. So let's talk about the student t distribution and some of its properties. To begin with, the graph is very similar to the standard normal curve. The mean is 0 and the distribution is symmetric about 0. The student's t distribution has more probability in the tail area than the standard normal distribution. The shape of the student's t distribution depends on the degrees of freedom. So degrees of freedom will be equal to the sample size minus 1. Now, as the degrees of freedom increases, the graph becomes more and more like the graph of the standard normal distribution. Using the student's t distribution results in a better estimate when the population standard deviation is not known. To calculate confidence intervals for the student t distribution, we need the following pieces of information. We need the standard deviation. We'll be using the sample standard deviation here. We will need the sample mean, that's our point estimate. We need the sample size, and we need a desired confidence level. So we need to do some extra calculations for the student t distribution. The confidence level and degrees of freedom together point to the t value that is used in the calculations. This t value can be found by using a table or by using a function that is on your calculator. Now, not all of the calculators do have this function, so we are going to practice finding it with the table as well. The TI-83 calculators do not have this function, while the TI-84s should have this function. This function is called the inverse t function, INVT function. It is found underneath the distribution menu where you found your inverse normal function and your normal CDF functions. So finding the correct t. To find the correct t that is needed for the confidence interval, you will need to first identify the sample size. From the sample size, you can calculate the degrees of freedom. Degrees of freedom is your sample size minus 1. Then you want to identify the area to the left of the t value you want to find. For example, if you want a confidence level of 95%, then the area to the left would be 1 minus the ratio 1 minus 0.95 divided by 2. It's the same formula that we had earlier on this chapter for the area to the left. Now, to find a t on a calculator, you would use the inverse t function, enter the area to the left, and then the degrees of freedom. This function is found under the distribution menu, so second bars would be what you would want to press. This function is not on the TI-83. To find t on the table, you will need to access the table and find the appropriate column and the appropriate row for the area to the left and for the degrees of freedom. Some tables, instead of saying area to the left, might just list the confidence level. So if we were using a 95% confidence level with a sample size of 16, what would we want for t? Well, 1 minus the ratio 1 minus 0.95 divided by 2 equals 0.975. And then degrees of freedom is 16 minus 1, so 15. So looking at this table here, we find our t value, we find our degrees of freedom, so that gives us 2.131. Also using the inverse t function, with our area to the left and our degrees of freedom entered, we come up with the same number, 2.131. For a 90% confidence level with a sample size of 26, find the critical t value. So looking at our table, our degrees of freedom is 25. Our area to the left is going to be 0.95. So we get a critical t-value of 1.708. So let's actually find confidence intervals for the student t-distribution. We'll need a slightly different formula though. So the formula we would use when calculating by hand will involve a t instead of a z, and it will have s for the sample standard deviation instead of sigma, the population standard deviation. Otherwise, our formula looks pretty much the same. Again, though, we don't want to answer like this. Statistics is about presenting information to the public. So we're going to answer with this fill-in-the-blank sentence that we saw earlier. Suppose you do a study of acupuncture to determine how effective it is on relieving pain. You measure sensory rates for 15 subjects with the results given below. Construct a 95% interval for the mean sensory rate for the population, which is assumed to be normal, from which you took the data. So we're given these 15 data values. If we want to do a confidence interval, we need a sample mean and a sample standard deviation. We know how to find sample mean and sample standard deviation. It's been a little while, so let's review it. We could enter these into a list and then use the one-var stats function, and that would give you a sample mean of 8.2267, a sample standard deviation of 1.6722, a sample size of 15, which means the degrees of freedom is 14. And then if we wanted a confidence level of 95%, the area to the left is 0.975. So our interval, writing it out then, with a t of 2.145, we would have our sample mean minus our t-value times the ratio standard deviation divided by the square root of the sample size. And then sample mean plus t-value times the ratio standard deviation over the square root of the sample size. So we're saying I am 95% confident that the population mean for sensory rates is between 7.30 and 9.15. Now again, we can do confidence intervals on the calculator, and I do want to encourage you to go ahead and use these functions if you have them. The calculator can have you input your standard deviation and mean and sample size and confidence level, or if you have a list of data values like we did in the last example, you can put your data values into a list and then tell the calculator that you have data that you've entered instead of entering the statistics. So the function you would be using on a TI-83 or 84 calculator would be the t-interval. Both of these calculators have this, and you'd find it by going to Stat, over to Tests, and then scrolling down a ways. Looking at example 4, assume that a sample is used to estimate a population mean. Find the 80% confidence interval for the sample size of 23 with a sample mean of 53.2 and a standard deviation of 14.1. Using the t-interval in the calculator, we would enter these values. You would receive the output, and you would write the sentence, I am 80% confident the population mean is between 49.32 and 57.09. Now, the biggest question here is how big of a sample are we going to need in order to have a certain level of confidence while having a fairly small margin of error still? We know that the larger the sample, the more accurate the sample statistic will be at predicting the population parameter. We also know that when we know the population standard deviation, we can determine the minimum sample size needed to be within a set margin of error at estimating the population mean. The caveat here is that we have to have the population standard deviation in order to calculate the sample size. That's because the z-value does not depend on the sample size, whereas t-values do depend on sample size. So we will be using the standard normal distribution. Now, to get the formula for sample size, let's revisit the formula for the confidence interval when using the standard normal distribution. So our maximum error to either side is z times sigma over square root of n. So if we're trying to solve for n, we would have n equals the ratio z times sigma over e, the whole thing squared. Now we're always going to round up here. This n is the minimum that we must sample, and we need a whole number for our sample size, so that's why we always round up. Let's look at an example here. The population standard deviation for the age of Foothill College students is 15 years. If we want to be 95% confident that the sample mean age is within 2 years of the true population mean of Foothill College students, how many randomly selected Foothill College students must be surveyed? Well, using our formula, our z-value would be 1.96. Our standard deviation is 15. We want to be within 2 years. So 1.96 times 15 divided by 2. We'll then want to square that. So simplifying, we have 14.7 squared, which is 216.09. We have to round that up. So we're going to go up to 217 students must be sampled. A researcher is trying to study the lifespan of certain species of bacteria. A preliminary sample of 25 bacteria revealed a sample mean of 64 hours with a standard deviation of 6 hours. He would like to estimate the mean lifespan for this species of bacteria within a margin of error of 0.5 hours at a 99% level of confidence. What sample size should you gather to achieve this? Now we know our formula, so we know that we are going to need a z-value first. So the z-value for a 99% level of confidence is 2.58. Now we need sigma, the population standard deviation. Since we're not given a population standard deviation here, but we are given a standard deviation from a previous study, we can assume that the standard deviation from the previous study is approximately equal to the population standard deviation. The maximum error that we wanted here was 0.5 hours. So plugging everything in, we see that we need a sample size of 959. Now we've spent all of our time so far talking about means, so let's spend a little bit of time on proportions now. So confidence intervals for population proportions. So sometimes a mean is not the correct tool to talk about a set of data. Many times a proportion can be used instead. You would use a proportion for talking about the people who voted yes, people with blue eyes, trees under 25 feet tall on campus, etc. For each of these, a mean doesn't really make sense, but the number that have the trait we want out of the total number sampled, that proportion would make sense. So proportion P is equal to x over n, where x is the number with the desired characteristic and n is the sample size. So what calculations are going to be necessary for a confidence interval for proportions? Well, we're estimating the parameter p. Our point estimate comes from p hat, which is the number that had our desired characteristic divided by the sample size. We also will need q hat, which is 1 minus p hat. Q hat is the proportion that did not have the desired characteristic. And then we'll end up using the standard normal distribution for our confidence interval for proportions. So the same z values we found before are going to work here. We do have a formula that works well for calculating this by hand. P hat minus z times the square root of the ratio p hat q hat over n. And then p hat plus z times the square root of the ratio p hat q hat over n. Again, we don't want to answer like this though. Statistics is about presenting information to the public. So we're going to answer with a sentence. This nice fill in the blank sentence still works. So I am blank % confident that the population proportion of or for, fill in what you're talking about here, is between your lower bound and your upper bound. So let's take a look at an example. The Berkman Center for Internet and Society at Harvard recently conducted a study analyzing the privacy management habits of teenage internet users. In a group of 50 teens, 13 reported having more than 500 friends on Facebook. Find a 90% confidence interval for the true proportion of teens who would report having more than 500 friends on Facebook. So we need to find p hat first. P hat is the number that do have more than 500 friends on Facebook. So 13 out of 50, 13 over 50. And then q hat would be 1 minus that, so 37 over 50. With a confidence level of 90%, our z value would be 1.65. So we have this formula all written out with our numbers plugged in. That gives us 0.1576 and 0.3624. Now, I don't advise plugging everything into your calculator all at once, trying to get this answer. Oftentimes, you'll run into issues with not using parentheses appropriately. So try to break this down and do it in pieces in order to get to the correct answer. But our final sentence would be, I am 90% confident that the population proportion of people with more than 500 friends on Facebook is between 0.1576 and 0.3624. Now again, you can do all of this on a calculator if you desire, and I do encourage you to be familiar with that, but understand that you have to be careful as you are plugging things in, using the correct functions and all of that on your calculator. But a confidence interval for proportions with a standard normal distribution function would be 1 prop z int. This again is found by going to stat and then over to tests on the TI-83 or 84 calculators. The calculator will ask for the number with the desired characteristic, so x, for the sample size n, and for the seed level. Out of 400 people sampled, 248 had kids. Based on this, construct a 95% confidence interval for the true population proportion of people with kids. Using 1 prop z int on the calculator, entering that x is 248, n is 400, and the sea level is 0.95, you'll receive this output. So we would state, I am 95% confident that the population proportion for people who have kids is between 0.572 and 0.668. Now, again, can we answer the question, how big of a sample is needed? The answer is yes, we can answer that question. So again, determining sample size, we know the larger the sample, the more accurate the sample statistic will be at predicting the population parameter. For proportion problems, we do not need any information about the population to find the sample size needed. We just need to know our desired confidence level and the margin of error that we are willing to allow. The formula does ask for p hat and q hat, but if we don't have an estimate for those, then we can always set each of them equal to 0.5, because that would maximize p hat times q hat. Again, we're going to start with the formula for the confidence interval, and we'll use that to figure out what our sample size formula should be. Our maximum error is equal to z times the square root of p hat q hat over n. So solving for n, we get z squared times p hat times q hat divided by the maximum error squared. Again, we're always rounding up because n is the minimum that we want to sample, and we do need a whole number for our sample size. Suppose a mobile phone company wants to determine the current percentage of customers who are 50 plus who use text messaging on their cell phones. So we would want a z-value of 1.65. Our maximum error is 0.03. And our p hat and q hat, we would set both of them equal to 0.5 because we do not have an estimate. So that tells us that we would need to sample 757 customers aged 50 plus to find the proportion within 3 percentage points that do use text messaging on their cell phones. A political candidate has asked you to conduct a poll to determine what percentage of people support her. If the candidate only wants an 8% margin of error at a 98% confidence level, what sample size is needed? Again, we're using this formula. Our z value here will be 2.33. P hat and q hat will set each of those equal to 0.5, and our margin of error E is equal to 0.08. So we find that we need to sample about 213 or more people. There are a few limitations that we do have with our confidence intervals. We're never going to be guaranteed the population parameter that we are estimating is actually in the interval that we constructed. The more confident that we wish to be, the larger the interval is going to be. And in order to have a high level of confidence and a low margin of error, we will need a very large sample size.